Hello everyone and Happy New Year. My name is Sanga Emmanuel and I'll be presenting on the working principle and the experimental plan for experiment 4, which is a spray dryer. So the main working principle for the spray dryer is the principle of atomization. In this principle, the formation of sprays having a required droplet size distribution is very important to any successful spray dryer operation. So that or in order for the powder specifications to be achieved. Atomization is created by either a rotary atomizer or spray nozzle atomizer. The location of the fluid bed within the drying chamber achieves the drying at lower temperature levels. It results in a higher thermal efficiency and cooler condition for powder handling. There are four main types of atomization, which are the centrifugal, the nozzle, pneumatic, and sonic atomization. So, for the centrifugal atomization, this uses a rotary disc, a rotating disc, or a wheel to break the liquid stream into droplets. So, this device normally operates in the range of 5,000 to 25,000 revolutions per minute with a wheel diameter of 5 to 50 centimeters. For the nozzle atomization process, the it is actually the second most common form of atomization, uh, which is also known as a hydraulic pressure nozzle atomization. Here, the liquid is pressurized by a pump and forced through an orifice to break the liquid into fine droplets. We move to the next the atomization, which is the pneumatic atomization. This is the third most common method used primarily in smaller drying systems, which is also known as the two fluid pneumatic atomization process. Here, the atomization is accomplished by interaction of the liquid with a second fluid. Usually, the second fluid is compressed air, and neither the liquid nor the air requires very high pressure, with about 200 kilopascals to 350 kilopascals being the main advantage of this form of atomization. And also, for the last atomization process, we have the uh, sonic atomization. Here, this type of atomization employs the use of ultrasonic energy, where the passing of liquid over the surface is vibrated at ultrasonic frequencies. So moving on with the working principle, I'll share on the dryer configuration and its contribution to the performance of the system. So the atomized droplets, which are formed from the atomizing device, have a velocity and direction initially established by the atomizer. It is necessary for the heated gas to mix with the cloud of droplets, then begin vaporization and influence the movement of the droplets inside the dryer so that they can dry sufficiently and do not stick on contact with the dryer walls. This is accomplished by placing the atomizer in or adjacent to a properly designed air disperser. So there are three main types of configurations which I'm going to discuss about. Uh, the three main types of configurations are the co-current, the counter current, and the mixed flow configurations. For the co-current configuration, the drying air and particles move through the drying chamber in the same direction. The product temperatures on discharge from the dryer are lower than the exhaust air temperature, and hence this is the ideal mode for the drying heat sensitive products. When operating with a rotary atomizer, the air disperser creates a high degree of air rotation, giving uniform temperatures throughout the drying chamber. However, an alternative non-rotating airflow is often used in TOA or the filter mate type spray dryers using nozzle atomizers with equal success. For the countercurrent process, the drying air and particles move through the drying chamber in opposite direction. This mode is suitable for products which require a degree of heat treatment during the drying. The temperature of the powder leaving the dryer is usually higher than the exhaust air temperature. And now for the mixed flow process, the particle movement through the drying chamber experiences both co-current and counter-current phases. This mode is suitable for heat stable products, where coarse powder requirements necessitate the use of nozzle atomizers, spraying upwards into an incoming airflow, or for heat-sensitive products where the atomizer sprays droplets downwards towards an integrated fluid bed. The air inlet and outlet are located at the top of the drying chamber. This is a sample video which demonstrates the operating principle of the spray dryer as shown.
Beverages may not only quench your thirst, they also enhance the flavor of a meal. Many beverages are in the form of powdered drink mix designed to be prepared by mixing with a solvent, usually water. An equipment known as the spray dryer is used to manufacture drink mixes. This is a conventional spray dryer. Spray dryer is widely used in industry to produce dry powder from slurry. Slurry from the mixing tank is introduced to the drying chamber through a rotary atomizer at the top. At the same time, dry air is heated to high temperature by a heater. The heated air is then introduced through an air disperser which is mounted around the atomizer. The rotary atomizer then breaks the liquid into tiny droplets and disperses the slurry droplets into the heating chamber. Atomization is important here because it creates greater liquid surface area for maximum contact between air and liquid droplets. The atomizer will produce a liquid mist where it leaves the atomizer and be distributed over the drying chamber. Now let us focus on the drying chamber. The hot air flows in a rotational movement and hence it is evenly distributed in the whole chamber. When the hot air is in contact with the liquid mist, fast evaporation of solvent begins. When solvent evaporates from the droplet surface, solid particle forms and falls to the bottom of the drying chamber. The hot drying gas flows through the spray drying chamber and carries the product to the cyclone. Powders are then extracted from the cyclone and the hot drying air is eliminated to the atmosphere through a suction blower. The advantages of spray dryer are, the dry particle size can be easily controlled. Many heat-sensitive products can be spray dried easily at relatively high inlet temperatures. Short residence time is required. Minimum overall flavor loss in the food industry. Lastly, it ensures high product quality. The disadvantages of the spray dryer are, the equipment is very costly and bulky, cleaning is time-consuming, and lastly, a lot of heat is wasted as it has low thermal efficiency. An example of industrial application is the production of orange juice. The operating conditions are, inlet air temperature, 180 to 250 degrees Celsius, outlet air temperature, 80 to 115 degrees Celsius, inlet moisture content, 75 to 85%, outlet moisture content, 3 to 3.5%, range of particle sizes obtained, 80 to 400 micrometer, spray rate, 2,290 kilograms per hour, airflow rate, 31,500 kilograms per hour. Nozzle pressure 700 to 2,500 psig.
Moving on to the experimental rig and setup. The experimental setup is as shown in the picture. Here we can see the different components of the spray dryer. We have the spray nozzle, we have the heater, we have the air filter, the drying chamber, the cyclone, the product collector, the control panel, we have the power supply, we have the feed tubing, and the area for the feed picker. And just to take note that the feed used in this experiment is fresh milk. In continuation, we have the experimental procedure, which ascertains both the experimental startup and the shutdown procedures. For the experimental startup, we have the procedures as follows. Uh, we ensure first that the electric blower should be connected to the cyclone collector with an appropriate duct, and that an appropriate receptacle is placed below the product outlet. Then we start the electric blower and open the main valve shutoff valve. Then we open the pilot gas valve and light the pilot burner. We then adjust the part low temperature control to 200 degrees Fahrenheit, and the burner is pressed on button and the flame is checked through the burner observation port. When the drying chamber outlet temperature, which is approximately about 180 degrees Fahrenheit, we then begin to add small amounts of the feed. First of all, the air valve is open, then the water feed valve is open. Here in this case, we don't yet add the main feed, which is the fresh milk. Here we add first the water feed. Then the part load temperature is adjusted to an appropriate level for the process. And also take note that food and most organic materials generally require a drying temperature in the range of 300 to 500 degrees Fahrenheit, while other require higher temperatures up to 750 degrees Fahrenheit and others up to 1000 degrees Fahrenheit. Uh, we then adjust the water feed rate to maintain an appropriate outlet temperature. And when the steady state temperature is attained, the water feed is switched to the slurry, which in this case is fresh milk. Atomization then is observed and the feed air is adjusted as required. The burner temperature and liquid feed rates are varied to achieve the desired product specifications. So when the objective is attained and our product is achieved, we then perform the shutdown procedure, which involves the following. First, the liquid feed is turned off, and then some water is run through the nozzle to clean it out, and the water feed is turned off, and then the air feed. So the burner is then shut down and the main gas shutoff valve is closed, and the electric blower is allowed to run until the equipment has cooled down or cooled off. The electric blower is turned off and the drying chamber door is open to inspect. And if the chamber requires cleaning, the electric blower is turned on and the material is brushed into the chamber outlet. And if the chamber requires washing, we clean with the water, and the liquid drain valve is open in order to evacuate the water from the system. Thank you. That will be all for my presentation.